Hi, I'm Tom and I talk about code. Welcome to another Rust programming livestream where today we are working on my compiler. Now, the language is getting to a pretty good point. I'm writing code, it looks like real code. I've got a little harness where I can build and run programs, and I've got a virtual screen that I can draw to. So a couple of streams ago we tried drawing to the virtual screen, and there were a couple of annoying things. And today we're going to try and do it again. So I'm gonna jump up into a file called fill.s. I don't know why I've gone for .s as my extension, I just had to pick a letter. S is already used for something. I think like some kind of like object file maybe. Anyway, we're just gonna write in here, okay? Actually we're not gonna write in here. We're gonna call it fill.prog. Except we're gonna edit this instead of remove it. Okay, because .s is already a thing and Vim's trying to use a different some kind of strange file format for this. So we're going to write a program. We're going to write a main function. It's going to put something on the screen. So let's pick two coordinates. Let's let x equal 5. Let y equal out of 40. Let's put it halfway down the screen. In fact, let's pick the midway pixel plus 1. Let's pick the midway pixel, 1919. This is like halfway across the screen rounded down. Okay? And that sounds good. My audio is clipping a little. I need to calm down just a little. I'm so excited about drawing to a virtual screen. So we have this x and this y coordinate, and now it would be really nice to be able to say let offset equal x times y, but we don't have a multiplication operator, so we have to write our own janky software multiplier. We'll write a function called mult, which takes an a and a b. We'll have an out parameter, which we'll call 0, and we'll have a counter parameter, which we'll call, or a counter local rather, which we'll call 0. Then we'll say while counter less than b, counter is less than b, out equals out plus a, return out. Up until my previous stream, you used to have to finish while, or maybe the stream before that, you used to have to finish while statements with a semicolon, but no more. We are out of that strange, unpleasant place. Okay, so we've written a crappy little software multiplier, x, y, and then we're gonna call a function called putPixel. We're gonna give it the offset, and we're gonna give it a color, which is gonna be 1 for now. So let's write this function. This is gonna be a void function, put px, int offset, int color, and we're gonna get an address. We're gonna say let adder equal whatever our screen offset is plus this offset, and then we'll set the memory address of this pointer to our color. Beautiful. Now, we probably want this to be a car pointer so that we only write a byte here instead of a word. That would be nice. Actually, this should probably be a car, not an int. Beautiful, beautiful. Okay, so this is my janky C-like language. Let's see what happens. We also need to return something here. Let's return 0 because we succeeded. Actually, let's return a number that's really distinct so we know something happened. Let's return 52. There's no mistakes with the number 52. So let's compile this. Let's just clear this screen real quick. Cargo run lang, and then we need to pass this -a flag because we do, and we need to spell cargo right, not Crago. Okay, a couple of problems here. What went wrong? We have an undefined variable. Now, instead of this magic screen, I'm just going to call this 0xc1000. This is a hexadecimal literal. We added these in the previous stream. That was pretty exciting. You used to have to write things out in decimal before that. That was a bit painful. Now this works. So we're going to xclip selection C. We're going to copy this. We're going to jump into my playground. We'll paste this in. We'll enable the screen. We'll hit build. And we'll run this and it'll work. Maybe. Or it's gonna like crash the web browser because I'm trying to bring up the console and nothing's happening. I can't click on anything here, okay? My computer fans are going a bit crazy. So that was fun. I wonder what caused that. Well, this is nice. This is just the example program. I need to actually paste the full program in. So if I run this, what does this look like? Looks like there's just a lot of stuff happening. Just a lot of stuff. Now I wrote this logging memory, this logging JavaScript memory thing, and I wonder if this is contributing to the fact that this is shitting the bed, or if I just, oh my god, this is really, it's cruel. My whole computer is slowing to a crawl. It's a little bit unpleasant. Here we go. Okay, what's happened? My window manager now has somehow shat the bed. This big gray blob, I don't know what this is. Okay, so that's not good. I don't know a lot of things, but my gut says that's probably not good. That might actually be a bug. So let's do this one more time, but let's actually step through and try and work out what the hell is going on. And I think I know what's going on, but let's see if we can work it out. Let's see if it happens while we're here, because this kind of happened the other day when I was trying to do this, and it kind of happened off camera recently too. So we're going to step through. We're in our main function. We have labels now as we're stepping through, which is phenomenal. Annoyingly, the buttons are stuck up here and the code goes all the way down here. So we're going to be in a situation where we're going to have to scroll all the way up here and then scroll down to see what's going on. But we'll cross that bridge when we get to it. So we're putting some values in registers. We're setting locals here, I guess, 19. We should do that twice, 19, yep. And then we're going to call a function, and that's going to happen down here when we set the program counter to 170. That is likely the address of the multiplication function. So let's go, wait, hold on. My brain's doing a thing. I really need to add for loops. I keep doing this. I keep writing while loops and then forgetting to do this stuff. This is like the 4th or 5th time this has happened. It's really strange. It's a really strange brain issue. But that actually explains why we loop forever. So let's just stop stepping through this manually. I realized what had happened. My brain caught up to like 5 minutes ago. Let's run this now, and that puts a dot on the screen. That's kind of cool, right? Now that's not where the dot should be. That's not where the dot should be. That's okay. That's okay. Now, what would be really nice is if I could set a breakpoint. I could say, okay, we're going to reset this, and we're going to run, until here, right? We're going to run until this instruction right here. When the PC is 66, we want to break. I can't do that, so I'm about to hit step a lot of times. I'm going to hit it, in fact, 19 times, however many instructions are in this inner loop times. Okay, so we're in the 200s, so we do a loop. This is maybe the first or second loop. Oh god, I think that was still the first loop. I think this is 2. Yeah, because you can see C is the counter here, so it goes to 3, I think. I think that's the counter. 76, 3, 4, yeah, that's the counter. So 4, so that's got to get to 19. What if we just make this like a smaller number? There's got to be a better soft multiply algorithm, right? There's got to be a better soft multiply algorithm. What if I just set this to 2? Okay, because then when we do this, we just don't have to click as much, and that's good. Even taking the time to stop and do that has saved me clicks. Okay, so we're gonna jump down here, and now I'm gonna click probably about 30 or 40 times. Thankfully, I have really high APM. I can actually get 2 hands involved here and like do a lot of clicking. 2, we're gonna see. Oh shit! I hit run instead. I was going for too much APM and I misclicked. There we go. That's the rhythm, right? Okay, so we're gonna see the counter. 1, 2. It's hard because we're also 2. There it is. Okay, so now this branch should jump back at some point to 66. We're looking for the program counter. We're looking for that to go back to 66. Back to 66. Step. Here we go. This is where it's going to happen. Okay, we push. We pop. We're down here. Where are we? Okay, it's coming. It's real soon. Yeah, we're resetting everything. 60. Okay, here we go. 66. This is where we're jumping. Ready? Here we go. Okay, so A. What's in the A register? 38. Is that 2 times 19? Yes. So that's good. That's good news. That's very good news. Oh, except that's not what I want. That's not what I want. I want 40 times y, and then I want offset plus x. So that's why the answer's wrong. The answer's wrong because I'm silly. Because I don't know how my own system works. Okay, that's fine. That's fine. It's one of those days apparently, but that's okay. Now that looks better. Now let's do the smart thing that we were trying to do from the start. Okay, isn't that good? Don't you love it when you write a programming language and then you forget how to write basic programs in that programming language? So that's a dot in the middle of the screen, okay? Relatively. We can put more dots, right? We can put more dots. But what we're gonna do first, let's just make this plus x. So then this is just offset. Okay, so then we're gonna grab this, we're gonna build, we're gonna run. For some reason that doesn't put a dot on the screen. See, and that's actually kind of troubling. Why does changing the line, like, what's going on here? How does this work? How have we ended up in this situation where the expression can be broken so simply, right? Similarly, if I put mult 40y in here, I feel like I'm also going to get a dot answer. Because there's something weird about my stack. There's something wrong with the stack. Okay? I don't even understand how it's possible that this happens. This wrote 2 pixels, and that just should not happen. What has happened here? How is this allowed? He can't keep getting away with it. I'm gonna also make this a pointer to a car. I think that makes more sense, okay? I think that makes more sense. Let's just... because this feels like it's writing a whole word, not just one byte. And that's weird. Indeed. How does this happen? How does this happen? How do we write 2 pixels here when we should only write 1? Well, the memory log will actually tell us a pretty good story here, right? So if I reset this and run again, we're going to see everywhere that we write. And we're going to see the C thousands, right? So if I search this for C000, I don't see it. Because... actually, I'm not sure why. Yeah, I'm really actually not sure why. That's a bit weird. We really should see, like, 0xC 1000. That address gets written to. I know it gets written to because I've mapped it in here. So why don't we log it? Now, there is this thing that I did in this file where set, I think I called it set log. I only enable logging when we're ticking the virtual machine. However, the reads and the writes to access the screen should happen in here. So that's okay. Oh, except it's not C1000, is it? It's CO something. It'll be CO, what number's this? 19 times 40. Let me just quickly do this. 19 times 40 plus 19. C1000 plus 779. And we want that in hex 49931. C3OB. Okay, let's do that. C3O 0xC. Anything that starts with 0xC. Anything here. Right at See, what's this? What are these addresses? Is this part of the stack? Supercricket says graphics. We have something. We have these weird fuzzy round pixels. I think I talked a little bit in a previous stream about how I can't work out how to scale. Like, I'm drawing to a 40 pixel by 40 pixel canvas, then drawing it to a second canvas scaled, but I can't work out how to make it not fuzzy and weird when I scale it. Hopefully we can do good graphics. Hopefully that'll happen. Okay. So what are these addresses? What's going on? Also, we're probably not writing 1, right? What I really need, you know, do you know what I'm actually going to do right now, okay? I'm going to add a multiply instruction just so that this is less stupid. Let's make it opcode F1213. I guess it's opcode 14. Let's say 15 just to be safe. Now I have 5 bits for this, so I can go up to 20, right? No, wait. Wait, how many bits? How many bits do I have? 5 bits, right? So there's 32 possible opcodes, and 32 is, yeah, hex 20. So I'm getting close to the limit. 20 Matthew 03, welcome. Welcome to the Rust compiler gang. We are building. Oh boy, we're building. And yeah, I like this graphics. Now that I'm affiliate, I need to get some Twitch emotes. I'm not totally sure what Twitch emotes I should get. I was thinking maybe, right? My vague plan right now is probably to have a bug, like a moth or something, for a bug. I thought that would be cute. I thought that would be a fun idea, right? Then when I make a mistake, people can just be like, bug. Yeah, so that's kind of the vibe I'm thinking right now, right? Things that are a little bit self-deprecating. Okay, so let's go into our VM. Let's implement this new instruction. Add. That would be cool. I've never seen anyone with a bug emoji. I tried pixel arting a moth myself, and I don't think my art skills are quite up to this task. But yeah, I don't know. I've got a short list of people I might pay to do it. We're gonna do this. We're gonna do the same thing. AB multiply. Except we're just gonna say A star B. I don't know what happens with overflow in multiply in Rust. We're gonna have a bunch of stuff break here, including that random stray character I had. Let's ignore that. Okay, apparently we're not gonna have a bunch of stuff break here, and that's kind of cool too. Let's go into the code gen and bin op. Cool. So if we have a binary operation, if it's, oh yeah, multiply, add and subtract we can all do on the stack. Multiply, we're gonna have to do a little bit more work. We're gonna have to say, well, we push the top 2 things off of the stack, right? So hold on, I need this. I need more than just one thing. I think I can say out.extend and then make an array here. I think that's better than what I've been doing. So let's go unresolved instruction, but just an instruction. And we're gonna say, it's gonna be a stack instruction again. We're gonna pop from the stack into register A, into register B, pop. Cool, and then we're gonna do the same thing into register C. So the first arg, C times, so the left hand side is C. So then we say unresolved instruction, instruction, multiply, into register C, we multiply C times B. It doesn't matter for multiplication, but I just need to get used to thinking about what the left hand and right hand side are when you're doing this kind of stack op. Now, I'm going to make this smarter at some point so not everything has to go through the stack, but for now, we're just really spamming out a bunch of unnecessary code for this, and then we push to the stack. That's the most important part, perhaps, where we push register C onto the stack. Beautiful. And actually, we can get rid of the curly braces. We don't need them. Okay, there's a couple of things going on here. Like that missing comma. What else have we got? Bin op. AST. Bin op. This is called multiply. Oops. And this is a register. Awesome. Can we now just do this? Surely that doesn't just work, right? What if I say 40 times y plus x? Surely this doesn't work. Surely there's... Oh, well, I need to make WASM too. Otherwise, it's not going to know what this mysterious multiply instruction is. Okay, we're gonna paste this in. We have a multiply instruction. That's kind of fun. That has literally never existed before. Let's get rid of this bloaty function, just so we're generating less code. We'll rebuild. We paste this in. This is a lot cleaner. There's a lot less going on here. That's nice. That is nice. All right, let's step over and see what's going on. Reset, step. This is no doubt yelling at me over an instruction that it doesn't know about, right? No? Step? No, we're going. We're cooking. I don't think I'd reloaded the page before, so I guess I just had to do that. And then it's like, hey. Oh, and 20 Matthew 03, thank you very much for the follow. Sorry, I missed that. I was so caught up in adding a new instruction to my VM that I forgot. But it's kind of cool. I love how easy it is to add an instruction like that. I can just do that off the cuff midstream. Oh, Cricket. He's found my mysterious default my default emote. Yeah, there. I also don't know why I got the prefix Tomar3. Are there other Tom Marxes on Twitch? Am I fighting them for the Tom Marx prefix? But yeah, they give you this like weird janky... I don't know, is this randomly assigned or does everyone just get that? I should have thought of this before I accepted affiliate. I feel like there's all this stuff I need to do now. Okay, so we're coming into our multiply, and this is very exciting. So C gets 40, B gets 40? These shouldn't both be 40. That's not right. Oh no, there we go. Sorry, C gets 19. So now we multiply these together into C, and that's correct, but they ended up in register B instead. I'm pretty sure 19 times 19 is 361. That feels right to me. 19 times 19, 361. Yeah, it kind of tastes like 361. Kind of tastes like 19. The problem is in my code gen, I forgot how this instruction works. The destination goes last, so we're gonna rebuild, recompile. Okay, if I run this, we put a dot in the middle of the screen. Nice. Now, do we have the same problem where if we say 40 times y plus x, that this no longer works? Okay. So that's almost disappointing because I kind of want it to not work, but I guess the function call is significant here. So we can play with that still. What is my experience as a developer? What was I doing before I started streaming? I mean, I'm very much barely a streamer. But yeah, I don't make any money from this or anything, right? I'm just messing around for fun. But I have been writing code since I was a young kid. I worked for the Australian Bureau of Statistics for a little bit. I worked for a big bank over here, and then I've worked in logistics tech for about a year. I'm currently unemployed, just goofing around and doing my own thing, which is fun. But yeah, just done lots of bits and pieces. My career's mostly in Java and Golang, but I've really enjoyed learning Rust lately. So yeah, just a lot of different stuff. I've never written a compiler before, definitely not like this. The most I've done is the Elements of Computer Systems book, which is a really great book. You should read it if you haven't. What is this? I want this one. I want the row. Okay. And let's see if we can return 40 times y. So let's see if this breaks now, right? Because there was something weird going on before. Get row y plus x. Okay. And I'm really hoping this breaks. What's really funny is... Oh, that's interesting. I wonder how this parses. If I run the compiler like this, I pipe the output to xclip, so I don't actually see there's a compiler error until I paste it in. So this is saying that right here it expects a semicolon. Right here it expects a semicolon. It does not like my function call in my expression. Does this work? No. Here, put pics. Weird. Says there's a missing semicolon. Oh, wait, hold on. Do you know what the problem is? Functions aren't allowed to have underscores in the name. This will work now. Yeah, this works. That's a really silly bug. Really silly bug. It's good. You're finding it hard to be really good at Java. Pro tip, being really good at Java is really hard. You can spend your whole career specializing in various bits and pieces of Java. Like, you know, just write good code. Rust is even more complicated. Yeah, but like programming's hard, right? You just have to be patient with yourself. You have to do, you know, a lot of work. I think people have told me a lot that I'm good at writing code, and it's like, well, you know, I promise that I've probably written more code than most people ever will, right? I'm one of those weird people that could work a full day writing code and then come home and still enjoy writing code. Okay, so we've replicated this same bug as before, where instead of putting a red dot, we're putting this weird smeary blue and white dot. And that's strange, and that really shouldn't be happening. So we're going to reset, we're going to step through this again, except because we now have a hardware multiply instruction, this is all a lot simpler. Way simpler. So we're going to step through until we jump, and we're going to see what happens to the stack. I actually have a stack visualization now, which is cool. I think that's very cool. Where's the multiply? Where is the multiply? Oh yeah, right, it's in here now. So we'll see a immediate PC 156 this. So we've pushed 19 and 19 to the stack, or 19 and... No, we pushed 19 to the stack. The stack's screwing this way. These are our locals, I think. Yeah, the stack's screwing this way. So we push the program counter? I don't know, that's weird. That's a weird number. And then it changes again. That's very weird. I don't know why that happens like that. Okay, cool. So then we jump. We jump down here. We're gonna grab into our C register. We're gonna push that to the stack. So now we have our two arguments on the stack. We are going to pop them into our B and C registers. For some reason, this is still kind of like a ghost value here, because the way this stack printing works doesn't really understand pushes and pops. It just kind of guesses based on the base pointer and the stack pointer, so it doesn't always guess right, but that's okay. We get the result in the C register, we push it to the stack, we pop it into the A register, and then we're going to start doing the return stuff. Okay, so we, add 6 to the immediate, so we're jumping back to address 62, which is here. Now we're going to push A to the stack, even though we just got it from the stack. We're very wasteful, basically. We're very wasteful. This is here twice for some reason. I don't fully understand this stack. I built this stack visualization. I don't fully understand it. Load word C0. So we push 19 to the stack again. This is for the addition, right? So we're resolving this kind of not recursively. Yeah, I guess recursively is the right way to think of it. So we push A to the stack. We stack 0. We add the two elements on top of the stack. Yeah, so this is 760 plus 19 gives us 779. We push the base pointer. So we have this extra ghost value, which is really annoying. You just kind of have to ignore this number. This isn't a real number. We have an argument, we have the base pointer, we have the old value for the program counter, except we kind of don't, because now we've moved the base pointer. It's gone. And then we jump. Okay, so what happens when we jump? We have to zoom out because the buttons are too far away from the code. So we are gonna load a stack offset. So this is getting a local. Oh no, sorry, that's an argument. Then we're gonna push it to the stack. So our argument is the offset from the screen. That's good. That's really good. We can deal with that. We can work with that. Then we're going to load our screen offset, which is this magic number. And we're going to push that to the stack as well. Cool. So we have the offset and we have the thing. These need to get added together. Okay, they're going to get summed. They're going to get summed. We're going to get there. So we pop into C. Yeah, we add them together, we pop into C. Cool. So this is the memory address we're writing to. This is C1000 plus the row plus the column. Okay. Now we're going to do a function call. And I see what's happened. I immediately see what's happened here. So let's look at this number in hex. Oops. C3OB. Okay, so what is C3 mod 16? And what is OB mod? Well, I mean, this is just OB, which is 12. 11. Okay, I'm off by 1. I'm off by 1 is fine. That's an acceptable tolerance for a programmer to be off by. 3 and 11. What are our colors that correspond to, if I just hit run, right? What are our colors that correspond to this? If I go to index color, if I go to hardware colors, so 0, 1, 2, 3, that is red, green. 0, 1, 2, 3. That's a blue, right? No, that's a red, green. That's like a purpley color. And then what's 11? Not that. So we're kind of off. Like this should be this and cyan, which is like, Okay, that doesn't quite add up. But basically what's happened here, okay? Essentially what has happened. What has happened is we've ended up with the wrong things on the stack. We haven't ended up like, actually wait, hold on, did I stop too early? I might have stopped too early. I know this is really annoying. I'm just gonna have to click through this again real quick. I might have gotten overly keen. This stack visualization is a little bit troublesome. Okay, so we're gonna jump again, and here we are. So we're gonna get back up to this point, right? And we can see this is on the stack. And actually, I think this is wrong. Because there's only one element on the stack here, then we have like our ghost stack, which is annoying. Bobbius, welcome. You missed the announcement because you were playing Noita. That's a cool problem to have. That's a pretty good problem to have. That's an acceptable reason. You know, there are lots of bad reasons to miss my stream, like working and you know, having dinner with a romantic partner. But playing Noita, I think that's acceptable. I think I'll allow that. Okay, so we push C to the stack. So this is the added offset. Then we're gonna load into C. Wait, load into. Let's take it C. C SP push. What's this number? C plus offset. Where does this number come from? What is this? Is the base pointer, right? That's not right. That's not what should be in the C register right now. This is bad. This is a red flag. So it feels like we forgot. It feels like we forgot to push 1 to the stack. Where does this 1 go? Where do we ever... Here, right? Here? What order do I function call? What order do I do the args in? I do them in reverse. So yeah, so 1 gets pushed first. Then we do all this stuff to call a function, which should push everything, which should do the rest of the stack. It really should do the rest of the stack. But somehow this is getting corrupted and we don't have the expected number of things on the stack when we proceed. So let's write a test case that highlights this. Let's go into our Lang tests and let's see if we can make a simpler test case that's gonna call this out. And let's write it without multiply. Let's write it so that it works without VM adjustments. Bobius, you missed me adding hard multiply. There's a hardware multiply instruction now. I don't know if I'm going to keep it, but it was just too annoying to live without, and so I added it in about 2 minutes, which is cool. It's cool that I can add it so quickly. All that macro work, it paid off. So, what am I saying? Stack shuffling. It's weird because I have a test that I thought covered this. Tests, functions. I thought... Actually, no, we have recursive calls, but we don't have complicated arguments. Actually, this is a function call test. Okay, so... Let's keep the multiplication function. I think that's kind of cool. I think soft multiply is extremely jank, and I think that's funny. But it definitely churns, right? It definitely churns the CPU, and like we're gonna be moving values around on the stack, so that's good. That's good. Let's let x equal 5, let y equal 7, and then let z equal 2, and let's say return multiply x minus 1 y, but multiply this, multiply x by z, then subtract 1, then multiply that by y. Yeah, I think that's what we want to do, right? This is what's breaking. This is where it falls apart. So 5, 7, 2. So 5 times 7 is 35, minus 1 is 34, times 2 is 68. So the answer should be 68. And this should break. We expect this to give us the wrong answer. Huh. Add with overflow. Okay, so we... Add with overflow. Add with overflow. VM 343, add with overflow. Oh my god, that's definitely not the right answer. Well, says that out plus 1, return out. Okay, well, something really weird is going on here. Can we wrapping add? Does that exist? It does. So now we're going to get a really funky answer. Yeah, okay. And like, that's good news. Is this just like way more code than should be executing? Perhaps. Perhaps it is. Which is funny, right? Because you wouldn't think any of this would be that hard to do. It did break. It did break. It broke much more violently than I ever could have. Oh, no. This makes perfect sense. This actually makes perfect sense, right? Because if you think about what this is, so let me go back to Python. Let's look at this in hex. CO6E. Okay. CO6E. Now, I have a feeling that I understand exactly what this is. When we run the program, we set the SP to 1024 times 3, so COO. That's 10 too short. Surely this is related to the base pointer though. Surely like one of these numbers, maybe we're multiplying something by the base pointer when we shouldn't be. I don't know. Either way, the base pointer from the stack is leaking into the function calls, which is bad. Vibane, hello, welcome. We've got a stack problem, the best kind of problem. Let's draw it, okay? Because drawing these stack problems does a lot to help us understand what's going on. So when we call a function, okay, we have a function called foo, and it takes an x and a y. Okay, so what do? We push y, we push x. Let me just double check I've got the order right. So push y, we do this. When we call a function, we push the base pointer, and then we push the program counter. And then the base pointer is becomes the old stack pointer. Okay. So in other words, our frame looks like this. So we have arg n ... arg o, the old BP, the old PC, and then locals. Okay. So what's happening is, when we end up doing this twice in a row, something breaks, right? So I'm going to have to do more simulation. I'm going to have to do more manual stack simulation. We need a second page for this. I need a smaller pen, a smaller, softer pen. Let's go 5. Is that too small? Perhaps. Okay, so because there's two functions here, the stack is getting poisoned somewhere, or the function is getting poisoned. Something is getting the wrong data. It's the stack. The functions are not balancing the stack correctly, or they're not returning to the correct place in the stack. I'm not sure. The stack pointer isn't being reset properly. So what happens, right? So let's draw this again, right? So arg n ... Actually, no, let's say arg1. Let's do this 2arg example, because that's what we have here. Arg0, we'll have bp prime, we have pc prime. I think I know what it might be. Right? Because if you imagine you do this, but then arg0, you build a new frame, right? You build a new frame, you call a new function. Yeah, okay. So let me draw this. So you have arg1, arg0, you have bp double prime, and you have pc double prime, which actually pc is like almost the same thing here. They're very similar values, but anyway, we'll call it double prime rather than trying to reason about this. Okay, so arg0 comes from the return value of the stack frame, right? So this returns, and the stack looks like, well, the stack should jump back to here, right? And then we push from here arv1. We're saying that arg0 is already up here, and then we'll push bp and pc, right? What I posit is happening is we're somehow ending up with this up here. It just doesn't really make sense, does it? But this is the value, right? This is the thing that's corrupting. It doesn't really feel right, does it? Something feels very, very sinister here. But the stack should get reset to right at this point after we do all of the stuff to evaluate the function that gives us arg0. So before we push arg0, that value is in the A register, right? Well, it's in the A register, yeah, from the result of that function. So the stack should look like this, and instead it looks like this. Right, it's got this extra thing in between. So when we call the function, we only end up with the latest argument and the base pointer instead of ever getting this first argument in there. Okay, so how does that happen? Oh boy, how does that happen? Maybe soft multiply is actually too complicated. Maybe we can make this happen with a simpler example. So let's make a function called foo. Let's go int x, int y. And let's just give back x plus y, I guess. We have to say return in this language, which is a bit silly. Foo. So x plus z minus 1 plus y. So this is 12, 11. Oh no, sorry, x plus. I mean, it doesn't matter. It's all commutative anyway. So it's 14. It's 13. Meant to delete. Oh, wrong scene, wrong scene. Every time, man. It's so frustrating. Thank you. Tested examines part of the stack. Yeah, it's hard to write tests that do that, but that would probably be a good idea. That would probably be a good idea. This does the same thing, funnily enough, and it actually doesn't execute that much code, which is interesting. Like, we should be able to step through and simulate it here, and it should be able to yell at us. But you're right. We should be able to like stop execution at some point. The hard thing is knowing where to stop execution, I guess. Because if like we can't just write a series of instructions, right? It's actually the code that's the problem. My stack is probably like the actual VM itself. Those instructions are pretty well tested. So I don't know how feasible it is to write a test that examines the stack without really tying it to the exact state of the code that is generated like today. And that's not really what I want. I don't want to be too bogged down in, writing tests that test that the generated code is exactly what I expect. If I wanted this to be an industrial compiler, I would have golden files, but that's a bit too tedious for me. I'm testing that the actual concept of these calls makes sense. So let's step through this. Maybe. Will this help? Maybe not. I really like that this gives me just the whole stream of instructions as they come out, right? This is kind of awesome. So we can literally step through this and simulate it by hand. Right? Like, we don't have to worry about the jumps. We don't worry about, this isn't, this is the linear set, the linear order of instructions that we run. Let's record a macro just to clean these up. Nice. Okay, so this is every instruction that was being run here. And we can simulate the stack along with them. So, do we really have to do this? I think we do have to do this. Oh my gosh. We don't have a lot of room. But let's simulate the stack. But quick debug, it lets you step. Maybe. I've got one, but the stack visualization is a bit jank. How can I improve my stack visualization? Visualizing the stack is kind of hard, right? Because how big is the stack? I guess I know where the stack starts. Okay, actually, you're right. You're right. That is a far smarter idea. Thank you. You just saved me going down a rabbit hole. I'm going to go into index, right? SP. I know where the stack pointer starts. I'm actually just going to print the entire... SP is... Well, the stack pointer is greater than the base pointer. The stack grows down. The stack grows... Oh yeah, hold on, that actually is fn push. The stack grows up. Push adds to the stack pointer. Pop subtracts from the stack pointer. I don't know why I've done this. It should probably go the other way. Anyway, that is not today's question. Why is my stack backwards? Phenomenal question. SP. Do we set the stack pointer here? Maybe we don't. Machine, new, halt. Okay, so where do we set the stack pointer? Where do we set the stack? Oh, we set that in the program. What am I doing? So the stack pointer, it's 1023 left shifted by 4. Where does that come from? That gets splattered out, so hold on. Which magical hex number is this? 3FFO. 3FFO. Let's just do this while I equals 3FFO. While I is less than or equal to the stack pointer, we're gonna add. Okay, so now when I come in here, we will visualize the entire stack. I think, hopefully, no? Do we get a visualization? Maybe? BP is not defined. Oh yeah. Started crafting interpreters, looked at my code, the way I do things is something very functional-esque. Do you mean in terms of the parsers? Because yeah, the parser is, like, the parser combinator stuff is very functional inspired. Yeah, the parsing, yeah, the parsing's good, flat. Yeah, I like parser combinators. They have problems. There are some limitations around error reporting, but you know, these things happen. Okay, let's reset this. Okay, so, So does crafting interpreters do recursive descent? Is that what Nystrom's about? I actually have the book and I haven't read it, and it's really silly that I'm doing my own project that touches similar territory still without having read the Nystrom book. But you know, I bought it. I'm glad I have it. Okay, so let's watch this stack. Okay, so this stack, this is the first stack index, right? I'm starting at the base of the stack, and then as the stack grows, it should grow towards the right. Now that was weird, right? Did anyone else see that? Did that look weird to anyone else? So I have all these 19s, and I don't know how we got so many 19s on the stack. This, I think I might see the problem. Let me just, let me, I'm just gonna really abuse this for a second. Hello, please press the correct key. Okay, so let's reset right off the bat. So we start, there is nothing on the stack. The stack pointer is actually 0, which is silly. So now the stack pointer is initialized, we straight away get a 0 in there. So we have this phantom value in the stack still. We push the program counter, we push the base pointer, we push the program counter, and I don't understand how that went in the middle. We had 2 zeros on the stack, and I have just pushed a value into the middle, right? Did that make sense to anyone else? Did anyone else, can we get an action replay of that value getting inserted into the... Okay, here's what I'm gonna do. I'm gonna go into my VM tests, and I'm gonna look at these stack tests and see what the hell's going on, because surely, I test this, right? I test this. Do I need to just write a test where I stress the machine out of it? I do a bunch of pushes and pops and just see if the thing on the stack is not what I expect. Did that seem weird to anyone else? Am I going crazy? What? Okay. So let's see what happens as I continue to click through this. Okay, let's see what happens. PC. Okay, so we add 4 to the stack. Okay, so this stack pointer jumps ahead because we now have room for locals. We push something onto the stack. That was correct. Okay, so basically just ignore one of these zeros. One of these zeros isn't real. Except when we pop it. Yeah, okay. Okay, so this is what's confusing. So I'm going to go back here. I'm putting one too many values here. So it actually needs to be less than, basically. The front of the stack is not relevant. So we're going to step. So now the stack is empty. This is correct, okay? This is what is on the stack, right? This is our stack frame. It has the program counter and the base pointer. That's correct. We add 4 to our stack pointer. This means we've just allocated room for 2 locals. So this is good. This is correct. This is correct. So we continue stepping. Okay, now we push 19 to the stack. This is good. We pop it off back into the register that it came from, which is very silly, but that's okay. We live with this inefficiency for now. That's why the value appeared in the middle of the stack, because it wasn't a push. It was a store word. It was a local. Okay, so that makes sense. We're setting this local to 19. Now we push. Now we do this silly push pop again. We load it into the C register, we push it, and then we pop it straight back off. Because I have no system that keeps track of which registers are being used for what. It's a very, very silly system. Okay, so we add to B, we store B here, right here in a local, which is correct, which again is correct. So that's good, that's good. This stack is looking immaculate. Now we've pushed our first argument in. So we're here, right? We've just done this part of this thing, basically. Oh no, sorry, we're here. We've just done this part. So now we're at the point here. Now we're going to start building our secondary stack frame that should resolve into this argument from the A register. Okay, this is it. This is where the action happens. So we load into C, which is one of our locals, I guess. We push it. We push it onto the stack. Okay, so this is an argument to a next function. So we're building, so this is the start of one stack frame, and this is now the start of a second stack frame. We're going to push the program counter and the base pointer. This is all good. This is all good. Then we add, we set the base pointer to the stack pointer, and we jump into this new function. So we have a new function. It has got an argument and the start of a stack frame. We don't have any locals, which is good. We load stack offset 3, so that's our argument. Then we push that to the stack. Then we do some other stuff. We push to the stack. We pop from the stack. We pop from the stack. We multiply 2 numbers together. Then we're going to push this onto the stack. Then we're going to pop it into the A register. It really makes you think about how silly all of my stack manipulation is. Oh boy, it's very silly. Okay, we're getting ready to do a return. We're getting so ready to do a return. Because we've got the old address. We've got the old address in the C register. We're getting ready. We're getting ready. Okay, so signed SP. So we're subtracting from the stack pointer. So something interesting is about to happen. We expect this to be left over. But that didn't happen. Okay. That makes a little bit of sense. Because now we keep going, right? Now we push the result. So these 2 values never get walked back. The stack never gets reset to where it was before this started. Okay, that makes sense. That makes sense, right? So we need to subtract 1. So what actually happens there, right? What actually happens? We add a signed immediate to the stack. We add the signed immediate 126. Now, 126 is, it's a 7-bit literal. So what's 126? Hold on. What is 126? Let me just think about this real quick. Hex 126 in hex. That's, wait, I can do this. 120, 64, 128. So 64 is 2 to the 2, 4, 8, 16, 32, 64. That's 2 to the 6. So 128 is 2 to the 7, because then, yeah, 256 is 2 to the 8. So 2 to the 7, that's 0, 1, 0, 0, 0, 0, 0, 0, but we're subtracting 2 from this, which is 0, 0, 1, 1, 1, 1, 0, 1. Is that right? Which would be 3, 8, 9, 8 plus 12, 13, D, E, F, 3D. Is that right? I'm going to double check this. I should have just done this in Python. Hex 126, 7E. I was slightly off. I was off by that, which is weird. I don't know what I did there. Maths is hard. Maths is hard, guys. I don't know if you know this. Let's just quietly erase that, okay? So we've got 7E, which is what I said all along. 7E. Okay. And this is good because this as wrong scene. Oh no, actually, what the hell? This is the right scene. Why does this hate me today? I was on the right scene. It just wasn't showing anything for some reason. That's weird. That one wasn't my fault. Every other time it's the wrong scene, that's my fault. That time it wasn't my fault. I just have to reselect the window sometimes. It's really annoying. Okay, so, well, that's good because I just did a bunch of maths that was wrong anyway, so you really didn't miss much. Oh yeah, that's better, isn't it? That's way better. Zymus, welcome. Thank you. Thank you. Doing that not in binary was a lot smarter. Okay, so 7E. Hex 80 minus, yeah, that makes a lot of sense. Oh, I was I was doing 64 minus 2. Anyway, which I guess is, hold on, I have to check that now. Well, yeah, hex 62, 3E. Okay, so I was off by 1. Hex 62 is 3. So I was off by 1 in the wrong power of 2. Cool. Okay, so anyway, what am I saying? This is a 2's complement 7-bit number, so this is so 1111111 is -1, and 1111110 should be -2, which doesn't seem big enough, right? Like we should be moving the stack back quite a lot. quite a lot. B0SP. Do I have a to-do about this? I feel like I'm going to look at this code. Yeah, wow. Oh, SP equals BP. Unsigned. Yeah, okay. So I see what's happened here. I know, we set the stack pointer to the old base pointer. So we restore... Do we restore the base pointer? Where do we restore the base pointer? Add immediate. Load previous base pointer. Yeah. Okay. So, we load the previous base pointer, which is here. No, wait, the stack pointer should be relative to that frame's. So like the stack prior to this. Okay, I'm going to reset and step through this again and get back to that state because that's really interesting. I didn't change thing. Oh my god, I'm really sorry, guys. I don't know what's wrong with my brain. Again, you're not missing loads. I'm chatting shit. I'm a bit lost. So it happens here, literally the next instruction. So the stack pointer is this, the base pointer is this, right? So the stack pointer and the base pointer are the same. The base pointer points to literally right here. So we need to subtract 4 plus 2 times the number of arguments to the function, which is fine. So we need to say let offset equals 4 plus 2 times the number of arguments to the current function. The number of arguments to the current function we're in. What is this in? Compile. No, we're in, yeah, okay. So, program pass offset for each, for P in program. Program is everything. Program is every top level element. So, if we're in a function definition body, we need to grab the, no, not a function definition. Yes, oh, this is copied and pasted, isn't it? Is it? Functions push. Well, okay, so we need it here too. This is the inline assembly version. I forgot about this. Args, so it's gonna be, we're gonna have to copy and paste this. Args.len. I'm glad I scrolled up a bit and remembered that. -1 times offset. Right, so 2, because we have to get rid of the whole stack frame. And then we need to subtract the number of arguments, and then this will be correct. We're going to copy this. Where else do we add msigned? We add msigned here. We're going to do the same thing. We're going to do exactly the same thing. 2. And I really hope that the number of... Wait, is that right? Block row arg. Compiled expert. Oh no, hold on. That's not the right place to put that. I went off half-cocked. Compile body. This is where I want to do it. This is where it gets harder. Define arg. Oh no, here we go. Function defs get name unwrap args. Let def equals. We just want to borrow it here. Function defs get name dot unwrap. Cool. So def.args, and we can do that. So we have this number 2, so we want to say let offset equal 4 plus 2 times def.args.len. And this is -1 times offset. We subtract enough, hopefully. Wait, what did that say, sorry? Okay, we'll -4, -4, subtract this, we'll get rid of this -1 because this is somehow getting to the wrong type. Neg not implemented for usize, that's because this has to be, I guess, an I32 or something. Then it'll complain about the same thing. Offset expected, I8 found I32. Yeah, okay, I guess maybe just turn this into an I8 for now. That works. It's not good, but it works. Let's go -4, -2 times args.len as I8. Just got to get the magical incantation of borrowing right. My favorite bug is where there isn't a bug and you don't understand your own code. Yeah. Like this happens. This is like a whole, it's like a layered cake of things that are maybe not actually bugs and are just me not understanding my own code, me not understanding how to build a compiler. But it's okay because we've got a compiler. Okay, so this is a problem. This is the borrow checker saying, hey, what the hell are you doing? Because I guess when we iterated over this, it just like was a different thing. what we actually need. Okay, where's compile body called? It's only called here and here. So we can pass this args. That's what we need. That's what we really need. We need a list of args, right? And that's a vec of, it's a good question. It's a great question. Args, identifier and type. So vec, AST, identifier, AST type. Okay, let's just solve this problem by passing more data in. That makes sense. In args, block.define arg, name. Perfect. Now we just say args.len. Now when we build this, it'll yell at me for not passing this through. And also because there's a delimiter that I haven't handled appropriately, apparently. Which is weird because it really feels like I have, what's it saying? Block compiler error 371. Okay, we have more things closing than we do opening, and that's because I put a semicolon there for some reason. That's silly. That's uniquely silly. Okay, now we're back in this problem, I guess. Oh, actually, hold on. We want this. We want to borrow this. Okay, here we go. So compile body, we just have to pass in the args. And the args, we just say args. We need to match for it. And then we're going to do the same thing down here where we say, oh no we don't. Args return type. So we still need the dot dot. Okay, does this break all my tests? This literally fixes all of my tests. That back of the napkin math, that really paid off. Okay, so let's recompile and edit and paste and run. And that puts a dot in the correct place. Holy crap. That was a journey. That was a real journey. So what if I really wasn't expecting that to work. I really thought there was going to be more, like a follow-on bug, but I guess that's fine. Maybe I'm a little disappointed. I don't know. Okay, well, let's start with x equals 0 and y equals 0, and let's say while there's no for loops. While y is less than 40, while x is less than 40, we'll do something, right? We'll put pix y 40 times y plus x 1. We're gonna paint the screen red. Then we're gonna x equals x plus 1, and we're gonna y equals y plus 1, and then we're gonna set x to 0. At the end, we're gonna go back to the start of the line. Then we're gonna return 52. Okay, cool. Get row can piss off. Are we about to fill the screen? Nah. I obviously have forgotten how to write while loops again. X equals x plus 1, y equals y plus 1. Have I forgotten how to write while loops again? Oh no, there it goes. There it is. It just took a second. It was just a lot of thrashing. A lot of messing around. So that's fun. Let's do different colors. Let's say C equals 0, and let's put. Actually, well, let's make it. Let's do it based on the row we're on, right? That's a cool pattern. Edit. I don't have a do. We're not there. So that's cool. That works, right? We can draw a bunch of weird colors to our screen. I love it. These are ANSI colors, by the way. I stole these colors. Nice. That's really exciting. That's so exciting. I don't know what this is. We'll ignore this. We'll ignore this translation error. That might just be, I don't know. Does that happen again if I run again? Yeah, okay. So we need to work out what's going on there. But other than that, right, this is beautiful. This is really good. Yeah, we really did actually blow up. Am I writing too many things? Let's just chill out. Let's do one less in each direction, right? Let's see what it says. Right, this is a good way to test, right? And actually, yeah, it's likely we're just running out of bounds by like 1. Programming is stealing with extra steps. Exactly. You are the LLM. Deep down, we're all just an LLM. But yeah, that's kind of nice. What other cool patterns are there? Let's go. Let C equals 0. We'll say C and then C plus 1. So every pixel gets a different color out of the 16. And I've got it set up so that if you write, like it's ANSI colors, right? 0, 1, 2, 3, 4, 5 up to 15, and then it loops around. So it's all just mod 16. Which is nice because it means there's less checks to do. I don't know why it takes so long to run. I might try disabling my weird JavaScript memory hack. Oh gosh. Okay. So yeah, we can see where the out of bounds stuff is occurring. Like that's what's causing the crash, this weird line at the side. And also you can see how ugly the pixels are because the scaling's broken. If you zoom out, it's kind of okay. But if you zoom in, you're like, oh, it makes you want to vomit. But also, like, you know, pixels aren't squares. Pixels are not square. That is a true science fact. People like to tell you pixels are square, and those people are lying. They are not telling the truth. They are not good people. Okay, so we've got some overflow that we need to address. And that might be a me bug, and that might be a not me bug, and it's hard to know for sure. Let me just quickly go into my JavaScript, right? And I'm gonna map memory. Yeah, I'm gonna map memory array instead of map memory func. And everywhere we say setlog. Actually, no, let's screw it. That's fine. We can keep the calls to setlog. It's just that memory isn't mapped in to anything. So if I go back in, if I build, if I run, it runs a bit faster. It runs a bit faster when it doesn't hook into JavaScript for every memory read. It doesn't call a JavaScript function for every memory read and write. Now let's just reload the page real quick. And if I set the clock speed to say 99 and I run, the clock speed works down. So this is actually too slow, but also it's going to pick up speed. Let's just leave this running for a second. So there is... Yeah, exactly, right? Predictive model of your environment. So there's something broken with the clock that I haven't quite been able to fix yet, and it's a JavaScript issue, but the machine is going to run faster and faster as it goes, and this is a little bit too slow. This is a little too slow. Let's reload the page again. I have to reload the page every time I want to do this because otherwise the speed continues to pick up. Okay, there we go. So that's fun. We've got this little visualization. It's working. We can draw stuff. This is the start. I want to do a tile mapped screen, and that will mostly be JavaScript, right? I'll be doing the same thing. I'll be writing bytes to a certain place in memory, but it'll draw a tile instead of a pixel, so I'll be able to do font rendering, and maybe have some kind of like terminal. I have created an over-engineered loading bar in JavaScript JIT. Yeah. You know, everyone loves a convoluted loading bar. I think it's actually everyone in the world's favorite thing. So this is pretty cool. But you know, it would be fun, you know, to have like my vision for this eventually is that we have a website and it's like, hey, here's a pattern on a screen, like kind of inspired by TAS 100, right? Here's a pattern on a screen. Write code that generates that pattern, and the pattern really, like in reality, is just you know, a pattern in memory, right? So if you generate that pattern in memory, you pass the test and have people kind of compete, right? Who can write the smallest program? Who can do it in the fewest cycles? That would be fun. That would be really fun. That's where I'm picturing this going. That's what I want. So I need a better editor environment, better errors, and so many things. There's so much front end work to make that not dog shit. But for now, this is a pretty good start. this feels pretty nice. So I hope you've all had a fun time. I think that's probably where I'm gonna have to call it for today. I do want to try and do some longer streams, but it's hard. It's hard to find the right times in my day to do it. This has been fun. This has been really great. Now I am looking for people to raid. If you have any raid suggestions, I'm always happy to take them. Always happy to find cool new people to raid, because I don't watch a lot of Twitch, you know. Now figure out how to make the canvas less blurry. That is like, that's an off-camera problem, okay? That is me messing around with JavaScript for I don't even know how long. It always tends to be a little bit of a rabbit hole. But yeah, we're gonna work out how to make this not look garbage, because it looks pretty bad. It looks pretty bad. One of the people I've hosted in the past is writing some OCaml. We're gonna raid him. We're gonna learn about some OCaml. Okay, this is gonna be a fun journey. So come send this guy some love. Sounds like a lot of fun. We'll throw some stuff over there. Thank you everyone for watching. Thank you everyone on YouTube who's been watching. This has been a lot of fun, and I will catch you all next time.